The title of this presentation is What Sets the Dynamical Dependence of Tropical Cyclone Genesis and Size on Latitude? Dynamical Experiments in a World Where Cyclones Reach the Poles. So my name is Dan Chavas. I'm an assistant professor of atmospheric science at Purdue University in the Department of Earth, Atmosphere, and Planetary Sciences. And this is a presentation very similar to one I gave on October 1st of 2019 at the Cyclone Workshop in Germany. This is work done in collaboration with Chavas Reed, who's a professor at Stony Brook. Okay, so we're going to jump right in here. There are multiple existing hypotheses about how tropical cyclones or hurricanes work on Earth that depend dynamically on the value of the local value of the Coriolis parameter f. So we'd like to test those hypotheses here. Okay, so first we're going to step back and have a real quick primer here for how hurricanes work on Earth. So this is a map showing genesis points from 2000 to 2008 in green and tracks in black, superimposed on mean sea surface temperatures globally. This is from Goni et al. 2009. Just giving you a sense of where hurricanes form and move. Is that they typically form over relatively warm water in the tropics, though not at the equator. They typically move poleward and westward with time, which is more evident in the northern hemisphere where there are more storms. And then generally they tend to move poleward and often recurve with the jet stream as they get caught up in the jet stream, or they die over land or over colder water. And so there's, like I said, there are actually three hypotheses that we'd like to test here. The first existing hypothesis is that genesis rate increases with f. So it scales with increasing Coriolis parameter, which is to say it should increase with latitude, and this is in an absolute sense, moving away from the equator. And so this is captured in what is commonly referred to as a Genesis potential index. There's a few different ones of these. This is one shown here from Emanuel and Nolan 2004. There's also similar from Camargo et al. 2014. And so this is a product of a bunch of different parameters. And so what I'm going to highlight here is there's really a product of dynamical parameters and thermodynamic parameters, and we'll focus on the dynamic one, which is on the left, which is associated with the absolute vorticity eta. And we can break down the absolute vorticity as the sum of the planetary vorticity, which is just f, the Coriolis parameter, plus the relative vorticity zeta, which is associated with cyclones and anticyclones from the circulation of the atmosphere itself. And so in general, the planetary vorticity is really the dominant parameter associated with the absolute vorticity in terms of its variability in space and time on Earth. The second existing hypothesis is that the minimum genesis latitude is set by the minimum value of f, or more generally of eta, the absolute vorticity. And so that's shown here in that sliver that you can see where there are very few storms, or right around the equator. And so this really has less, I think, specific precedent in the literature, but a common statement that's been made in the past is that there's a requirement that the absolute vorticity of the airflow has a non-zero value. And so that might imply, for example, that what you need is some minimum threshold value of f or of eta at the center of the storm. And then third is that storm size, a measure of overall storm size, should scale inversely with f. So there's this current theory, and we also have what we call f-plane simulations, predict a 1 over f scaling for storm size. And so this is size on the y-axis, and there's a few different measures of it versus latitude on the x-axis. And so the issue with this is in direct contrast to observations, where storms tend to either be constant or get slowly larger as you go towards higher latitudes. So I've worked on both sides of this. So clearly we need a new hypothesis, and it's time to kind of bridge this gap a little bit better here. So one issue with testing these dynamical hypotheses on Earth is that on Earth, the thermodynamic environment rapidly becomes hostile to tropical cyclones, to hurricanes at higher latitudes. So this is just one example of a figure showing the climatological ventilation index, which is just a measure of tropical cyclone or environmental favorability for hurricane activity. So lower values means more favorable. So this is actually taken from a recent paper by my postdoc, Kim Hugowind. And so the black dots are showing you genesis points, historical genesis points, and then the lighter colors denote lower values of ventilation index, and the darker colors denote higher values of ventilation index. And so In general, what you can see, if you don't need to look at the details of this, is that in the tropics, so at low latitudes, the environment is generally thermodynamically favorable for tropical cyclones, for hurricanes. But then as you move poleward, things change very rapidly to become thermodynamically hostile to hurricane activity. And so, really, if we want to test dynamical hypotheses, this is actually really annoying. At a basic experimental level, is that we'd like to be able to avoid, to minimize this thermodynamic variability as much as possible to isolate the dynamical component. So let's take a step back and think about our rotating Earth and what external forcing, or what forcing there is for variability on a planet. So we have planetary thermodynamic forcing, which is solar insolation gradients and land, so generally variations in surface properties. And then we have planetary dynamical forcing, which is associated with the variation of F with latitude. So F is 2 omega sine phi, where omega is the rotation rate of the planet. So can we imagine a world without this planetary thermodynamic forcing? As I mentioned, that's annoying. We'd like to get rid of it. Okay, so what we're going to do is use, as our experimental laboratory, the NCAR's Community Atmosphere Model version 5.3. We run it at a 25-kilometer horizontal resolution globally, which is nice. It's fairly uniform globally. And so this is just an AMIP Earth-like simulation using historical SSTs and solar insolation for 1979 to 2012 as forcing. And so what we're looking at here, and all these movies I'll show, is just the near-surface wind speed in meters per second. So you can see there's a rich array of phenomena on Earth, including hurricanes. You see one here a couple of them forming over the Atlantic Ocean. And so, yeah, so we have a lot of things, including hurricanes, that typically form in the basins and areas that you expect them to form on the real Earth. So we can take this same model and do something very different with it, which is to cover the planet in water. We call it an aquaplanet, where we make that sea surface temperature be the same everywhere on the planet and make the sun shine the same everywhere on the planet as well. So this is something called an aquaplanet with uniform thermal forcing. Tim Merlis was the first to introduce this really in 2016. So here we have a 29 degrees sea surface temperature and solar insolation is 340 watts per meter squared. That's constant and a diurnal average everywhere on the planet. So what you get is something that's dramatically different, where the dominant phenomenon now is tropical cyclones. That's what you're seeing here are lots and lots of tropical cyclones. But what's amazing is they still form at relatively low latitudes. They still move poleward and westward with time, if you'll see some of them form. But in contrast to the real world where they'd run over land, over colder water, here none of those things that cause hurricanes to die is in the system anymore. And so they just sort of pile up at high latitudes and do all sorts of funky things interacting with one another. But importantly, they don't necessarily just merge into one giant hurricane or anything like that. So if you want to think very kind of abstractly or zoomed out view of this world, you have a cyclone sparse equatorial belt, and then that's sandwiched between two cyclone-filled polar caps. Okay, so what we're going to do now is take this world and do some planetary dynamical experiments and do two types. We're going to vary the planetary radius and vary the planetary rotation rate while holding all other parameters constant. And so why do we do this? So going back to our planetary dynamical forcing, we know F depends on the planetary rotation rate, though it does not depend on planetary radius, which is useful experimentally. And I'm going to propose that there's a second parameter that's important as well, a second dynamical parameter, which is what we call beta, which is the meridional gradient in F. So that's 2 omega over A cosine of phi. So I'm going to propose this second parameter is important, and specifically that there's really two length scales associated with these parameters that are important. So I'd mentioned before we have one length scale, which is this inverse F scale. That's a 1 over F scaling that we've had for some time. And so here I'm going to put in as a velocity scale in the numerator the potential intensity, which is a thermodynamic upper bound for storm intensity. And so that's nearly constant at about 70 meters per second in our simulations. And so I'm going to propose there's a second length scale, which is called the Rhines scale. And so it's sort of an inverse beta scale, but with a square root in front of it. And it's a length scale that governs wave vortex transitions. If you're much smaller than the Rhines scale, you tend to be, as an eddy, you're happy to be a vortex. And if you're much larger than it, then you're going to devolve into wave-like behavior. And so that's something that's been studied quite a bit. And so I'm just going to posit that there are these two length scales that are important. And you'll notice in particular that the inverse F scale decreases with latitude and the Rhines scale increases with latitude, and that's really important. So one increases and one decreases, which means that there's a point where they intersect, a single point that we call the critical latitude phi sub c. And you can solve for this analytically by setting the two length scales equal to each other. Okay, so we're going to work with these two length scales. I'm just going to argue that these are important. Okay, so we're going to do a bunch of experiments I mentioned. So we vary the planetary rotation rate. So the control is in the top middle, and then doubled rotation rates to the left, and then halved is to the bottom left, and then halved again is below the control, and then we have a doubled planetary size is in the top right, and a halved planetary size is in the bottom right. So those ones are obviously not drawn to scale. So this is just a chance to put them all on one screen because it's awesome, and also just to point out, you can probably see by eye there are clearly qualitative differences of varying kinds, but what I'll be doing is going in depth into analyzing these simulations. Okay, so let's get to it. Let's test our hypotheses using our experiments. So we'll start off first by looking at the first hypothesis, which is related to genesis rate. So we're going to start off just by showing you, to orient yourself, genesis rate on the y-axis, that's a count per unit area per year, as a function of absolute latitude on the x-axis. So we're combining both hemispheres since it's hemispherically symmetric. And what we've shown here is in the brown with the black outline is just our control aquaplanet simulation. And then in the light blue is the EAPS style Earth-like simulation. So you can see that in the control case, genesis rate increases to a peak near about 30 degrees, 30 degrees north or south, and then it decreases to 0 near about 50 degrees. And then at the high latitudes, there's actually lots and lots of hurricanes, and the tracker is not really able to adequately track genesis events. But that's not the area that we're interested in. And so you can compare this to the AMIP Earth-like present-day climate, where clearly there are many fewer storms. There's about 7 times fewer storms in the historical simulation than in the aquaplanet simulation, and the peak is shifted towards lower latitudes. Okay, so we can take our control simulation, which hasn't changed that brown curve, and we can plot all of our experiments, our aquaplanet experiments, all on a single plot. So you can see genesis rate as a function of latitude. And so it seems like just kind of a mess of a bunch of different curves. There's clearly variation across all the experiments. But so our hypothesis was not as a genesis rate not as a function of latitude, but as a function of f. So what we can do is map these results from latitude into f space. And so what happens when you do that is, so now we've changed the x-axis to be f, where notably f is varying across all the experiments. That's not a constant at any given latitude for the cases where we're varying the rotation rate now. And so something pretty remarkable happens is that you'll notice that there seems to be this kind of quasi-universal increase in genesis rate with increasing f across all of our simulations here now. And so what's interesting though is that the value of f where that peak occurs now seems to vary systematically across our simulations. And so first though, we'll just show that genesis rate you can see is in the black dashed line is a linear fit, and then there's a slightly nonlinear fit there as well. That doesn't vary too dramatically. And so just as an example, the slope of this line is about 0.7, which tells you the rate at which genesis increases with increasing f across our simulations. So notably, as I mentioned, the dot that shows where the peak actually occurs, that value of f seems to vary systematically across these experiments. And what's interesting is that value of f seems to follows quite closely the value of f at the critical latitude. So this is just really a direct indication, and I'll show it here, but we show this in the papers. This is a direct indication of the role of this interplay of these two length scales, the Rhines scale and this inverse f scale, as being important within the system, is here setting the value of f where genesis seems to peak. Okay, the second hypothesis we want to test is how close to the equator can storms form. So it's the minimum storm latitude. And the original hypothesis was that this might be some threshold value of f. And so we have to be a little more precise in this analysis. Before we did it we just binned things in 5-degree latitude bins. But here we really want to see how close to the equator you can get. So what we're showing here is, and the x-axis is longitude and y-axis is absolute latitude. And the curves here show the minimum absolute latitude of storm occurrence here in 5-degree longitude bins. So each of these curves shows is shown for each of our aquaplanet experiments, and then on the y-axis you'll notice there's a star marker that denotes, we use that to denote the median latitude of each curve, so we'll call that phi g naught. And so what's interesting is you can see right off the bat that this marker varies across all of our simulations, and that includes varying the planetary radius. And so that alone, you know that since f doesn't depend on a, f alone, some threshold value of f cannot be the explanatory parameter for how close to the equator storms can get. And so instead we can propose an alternative hypothesis, which is an equatorial Rhines or deformation scale. So here we're showing it as the Rhines scale. That's this equation in the bottom right, which is just the Rhines scale evaluated at phi equals 0, and that's shown on the x-axis of this plot on the right. And this is really indistinguishable from a deformation scale. They differ by a constant. So here we're just looking at scalings. And so on the y, we're going to compare this against the y-axis is the absolute distance from that phi g naught to the equator. And so this is important because this distance varies, particularly when you vary the planetary radius. Then a given latitude is not the same distance from the equator consistently. And so you can see that this distance from the equator, minimum distance from the equator, scales quite nicely with this equatorial Rhines or deformation scale. We can go one step further and throw on the EAPS historical Earth simulation curve in this light blue, and you can see there's much more zonal variability, which is not surprising because now we've introduced significant zonal variability that we see on the real Earth. And so what's interesting is, so the real world, you'll notice that the curve actually bends down towards the very near the equator, in the maritime continent and Indian Ocean regions. So this is regions where relative vorticity is non-negligible, and indeed we know on Earth that this is where the lowest latitude storms are often found. And so that actually deviates this marker in our predicted scaling away from what we get in our aquaplanet simulations, because now relative vorticity is important as well. So physically, what's the physical interpretation is this is really a measure, an indicator of storm size. So the storm circulation needs to fit formally within a region of like-signed absolute vorticity. So if you have relatively little relative vorticity, it just means on one side of the equator, but you can generalize that to say like-signed absolute vorticity. So it's not a minimum threshold value at the center of the storm in eta. Okay, so the third hypothesis is related to storm size, and so we're going to start off here again. This is storm size, the radius of 2 meters per second. So this is really trying to get a measure of the overall size of the circulation. So in kilometers on the y-axis as a function of absolute latitude on the x-axis here, phi. So again, we'll start off just showing control in the brown, and then the EAPS historical simulation in this light blue. And so what's pretty remarkable, first and foremost, is that storm size in our control simulation is quite similar to EAPS in the tropics and the subtropics. So we've removed all the heterogeneity of the real world, and we're getting something that's not dramatically or not qualitatively different in our simple aquaplanet simulation. And so notably, storm size tends to, there's an initial decrease at very low latitudes, and then it stays approximately constant or generally increases with latitude very slowly, which is, as we noted before, is very similar to observations. And then there's this deviation at high latitudes, where in the real world, storms undergo extratropical transition. They interact with the jet stream, and they tend to expand quite rapidly, which is something we're seeing in EAPS. But in the control aquaplanet simulation, where you have no jet stream and everything is thermodynamically homogeneous, storm size actually starts to decrease with latitude at high latitudes. So that's something we'd like to think about a little bit more. But first and foremost, so at low latitudes, what's notable is if we could just throw on a Rhines scaling here, you get this very gradual increase in size with latitude in the tropics or subtropics. So that suggests that This is a much better hypothesis for what's going on in low to mid, we'll say low to mid latitudes on Earth, or maybe generally an Earth-like planet. Okay, so we can go a step further to test that Rhines scaling, is to look as, here we can break up our experiments to be varying planetary rotation rate on the left, going from darker to lighter colors is from high to low rotation rate, and then on the right is varying planetary radius, where the green is a smaller planet and red is a larger planet. And so what we can do is to throw on some scalings here, so that we can look at a Rhines scaling at lower latitudes, and then I should have noted these dots correspond to the peak storm size in each simulation, and so we can throw on Rhines scalings up to the peak at low latitudes, and then an inverse F type scaling at higher latitudes relative to that peak. And so first, for varying planetary rotation rate, you'll notice is that size tends to increase with decreasing omega, and it actually, particularly for these first three simulations, size decreases approximately as 1 over the square root of omega. And you'll note at this very low rotation rate case, really, there's very few storms in this simulation, so I think there's a lot of, it's probably a lot noisier in those cases, or maybe something else is going on. And then similarly, on the right, we can also compare, do a similar Rhines and inverse F scaling with across our simulations, and you get that storm size in this Rhines scaling, this low latitude region, tends to increase with increasing planetary radius, and that also follows approximately an A to the 1/2 scaling. So these are both completely consistent with the Rhines scaling, so we really have a better test of whether the Rhines scale applies within our equatorial belt region at lower mid-latitudes. So at higher latitudes, storm size tends to follow approximately an inverse F scaling in the polar cap. So you should note, though, that this is relative to that peak. So it's not directly predicted from the theory. We're just assuming that at the peak, that storm size tends to decrease following a 1 over F scaling there. So notably, the transition latitude, this latitude of peak size, stays constant in the varying planetary rotation rate case, which is not what is predicted by the theory, but the transition latitude scales along with the critical latitude quite well, meaning it moves towards the equator as you go to a larger planet, so that's well predicted by the theory. Okay, so we want to take a step back and say, well, what the heck is the Rhines scale? What is this Rhines scale, and why would it limit tropical cyclone size? So the Rhines scale is kind of shockingly fundamental, but we don't really, in atmospheric science, particularly in weather and to some extent climate science, we don't really teach it at all, but it's quite fundamental. So this goes back to Rhines 1975. And it shows up, and it's the intrinsic length scale in the quasi-geostrophic vorticity equation, which is just reproduced here. And you can look at this, and this is discussed in detail in Vallis' his big book, 2017 book, page 446. Okay, so the Rhines scale really serves as kind of a transition length scale between two regimes. So if you're much smaller than the Rhines scale, you're in a vortex-dominant regime, which is to say the nonlinear term is really important. And what that means is that the time scale of eddy overturning is much smaller than the time scale it takes to produce a Rossby wave. So what that means is basically you just don't feel beta, and you're very happy as a vortex. In contrast, if you're much larger than the Rhines scale, you're in a wave-dominant regime, which means the beta term is important. And so what does that mean conceptually is that your time scale of eddy overturning is much larger than the time scale of producing a Rossby wave. So you're going to feel beta strongly, you're going to produce Rossby waves, and you're going to radiate those Rossby waves away. And so there's been a lot of work on the behavior of a barotropic vortex on a beta plane. Some of the references are provided at the bottom, and a key outcome of that is that this process acts to limit vortex size. And so it seems likely that this would act to limit the size of a tropical cyclone as well. So I have a student actually working on this as part of his PhD dissertation at the moment. Okay, so there's kind of a broader outcome of this that I just want to highlight, which is that I mentioned that as you go to a larger planet, you actually get a larger fraction of the surface that's covered in cyclones. And this is shown here, going from on the left is a smaller planet, going towards the right is a larger planet, so larger planetary radius, and you can see this visually. And so what's pretty cool is that this is actually predicted by the theory. And so this is, as you go to a larger value of A, what are you doing is that the inverse F scale doesn't change. It doesn't depend on A, but the Rhines scale does. The Rhines scale gets larger. So as you go to larger A, this Rhines scale curve is going to shift upwards. And so what that does is that acts to move this intersection point, this critical latitude equatorward towards the equator. And so that's exactly what's happening here as you go from smaller to larger planet. And so that's pretty wild because it says that the theory basically predicts that a large, internally heated Earth-like planet might have really insane weather. I want you to highlight that again. We're talking about a world significantly covered by hurricanes. And so it just would be a wild place to live. If you're thinking about the weather on a planet like this, you would be pretty routinely hit by hurricanes. It would be kind of wild to think about living on a planet like that. Okay, so just to summarize, I like to think of this generally as using imaginary worlds to understand tropical cyclones on Earth. So the first hypothesis was that we tested was that genesis rate really does increase with F, or more generally with eta, the absolute vorticity. The minimum genesis latitude is set by the need to fit the circulation on one side of the equator, or again in a region of like-signed absolute vorticity. So this is an equatorial deformation scale or an equatorial Rhines scale, not a minimum value of F. And now we have really a new, better hypothesis for tropical cyclone size on Earth, which is that in low to mid latitudes, you're really going to be limited by the Rhines scale. It's much smaller than this inverse F scale, and so the Rhines scale is really what's important. And again, I have a student working on this effect. And then more generally, just this idea that the behavior of tropical cyclones on a sphere is governed dynamically by the interplay of two length scales, so not just an inverse F scale, but also a Rhines scale. So this work, again, has been published in the Journal of Atmospheric Science, Chavas and Reed 2019. The citation is provided there. I'm happy to share this data with anyone who's interested in working with these simulations. So I think there's a lot of other interesting things that could probably be done with these simulations moving forward. So I'm going to finish just with a nice schematic slide. This is provided as the final figure in our paper that tries to give us a simple schematic representation of all the things that we found in this paper, because there's really a lot going on. So thanks so much for listening. Again, my name is Dan Chavas. I'm at Purdue University. Take care.